So we'll continue on with a little bit of the applications of mechanics, and more specifically, projectile motion. One of the things that we have a tough time understanding is that the horizontal component of projectiles is just like a horizontal component of an object rolling on a table. It doesn't change. If an object is launched horizontally at a certain speed, that is the horizontal distance. Whether that object is rolled across a table at 5 meters per second in the x direction, or if it is launched at 5 meters per second in the x direction across a room through the air. Now, some people usually will like, well, what about air resistance, Mr. Peterson? Air resistance is going to change that. You are correct. I'm glad that you know that. However, that opens up a can of worms. Okay? And it makes our lives much more difficult. So to make our lives easier, for now, let's just say, you know what? Let's not worry about air resistance. You know that it's there. You know that it affects everything that is launched horizontally through the air. We're good. However, mathematically speaking, let's not worry about it. Okay? The vertical component that an object has, whether it's falling down as if it were dropped, or if it is being launched up, is the same. Okay? Either or works the same. Like I said, you've solved for everything that we've covered. We've solved for objects rolling across a table. We've solved for objects falling from a 0 point. We've solved at what height will an object reach its maximum height if it was thrown up into the air. You've done that. Now we're just going to start taking those things and putting them together. It's just kind of, and you have to do it just as we did it in the classroom, little by little. Can't just try and go, well, here's here, just kind of find the means to the ends. No, you have to do it step by step. Okay, it's very important. As the object rolls off the table, we have different parts to it as it's going through the air. The part that we see is kind of the black dotted line, the trajectory. That's what we see the object go at. But to solve things, because that's a curve, and we're not doing calculus, we have to split it up into different components, an X and a Y component, because we can solve that. If we know what that initial velocity is when the object leaves the table, we know the horizontal speed throughout the whole part. If we know the height of the table, we will be able to solve for the vertical velocity as it goes down. And then take those 2 points and combine them using vectors and triangles to solve for the hypotenuse, so to speak. Because if I take and move this vertical component over to there to close my triangle, now it's, oh, you're like, oh, a squared, b squared, c squared. I can do that. And it's right. You can. So you can solve for these parts. So when we have this now, I'm going to, when I click the shoot, cannonball goes, we can see that the horizontal component of the cannonball doesn't change. The only thing that changes, again, is the vertical component, because as it is falling, it is accelerating towards the bottom because of gravity. It is constantly accelerating as it's going down. The horizontal does not change. It's bigger and bigger and bigger. If I pause this at any point, I don't think I can because it's a GIF, I would be able to see that those make a triangle. And then I could find the velocity that I would observe of the cannon through the air at any given time. So something to think about here. At the instant a horizontally pointed cannon is fired, a cannonball is held at the side and is released and drops to the ground. Which one strikes the ground first? The one fired from the cannon or the one that is dropped? This diagram, which we have seen, we've seen a diagram very similar to the first one and the last one in an assignment near the beginning of the class. And now we can see that no matter the angle, pretty much the distance is almost the same, as long as that horizontal is going to be a little bit is the same. Might be a little bit short, but not too far off. Still going to have a horizontal component to it as it's dropped and goes. Okay? Now, if an object is launched horizontally, the initial angle, the angle at which it is launched is going to be similar, dare say the same, as the landing angle that we have. Why do I say dare say? Because, well, you know, there's always those little things that could, variations that could potentially really change it. Right? But the angle that we have and are able to measure, here, is going to be the same, I believe, there. Why? This one's to the horizontal. That one's to the horizontal. It's just below the horizon, right? And this one is above the horizon. Now, things that should make sense as it's going through the air. What's happening to the vertical component as it's going through the air? Is it increasing or decreasing? Decreasing. As it should make sense. Because what's affecting it when it's being launched up? Gravity. It's like, no, you don't go that high. I'm pulling you down. Okay, remember, it's not the man, it's gravity pulling you down. And then at its pinnacle, in a very small moment in time, there is no vertical, is there? That's because now it's changing from slowing down to over here, it's now going to be speeding up. Because what's affecting it now? Gravity. But now instead of slowing it down, it's saying, okay, you're going to get faster coming towards back down to the earth. And it's that right there that's very important to us. Because mathematically speaking, if we have a 0 point, we can find the height that it takes. If I have a tough time, I can't find the time of this altogether without hitting a stopwatch and being there the whole time. I can calculate how fast it's going to fall if I got a height that it goes. How can I find the height that it goes? If I know the angle here, and an object is launched at a certain angle, can I find out what that is? Yes. Sine, cosine, and tangent. I have an angle. I can move that over to here, and now I complete a triangle. Opposite. This would be opposite of that. Oh, so the sine of that angle will give me the vertical component. I have the vertical component. Yahtzee. I know how high it's going to go. Once I know how high it's going to go, I can find out the time that it's going to go. Once I know the time that it's going to go in the air, I can tell how far it's going to go. How do I know? What doesn't change as it goes from left to right? Gravity doesn't change, that's up and down, it's always there. But the velocity does not change as it goes from left to right. If I have a time and a velocity, how would I find that horizontal velocity? Oh, cosine of that angle. Because that's adjacent. I would have a cosine. I have the velocity in that direction. I know how far it's going to go. How do you think they're able to predict how far a baseball is hit in a stadium? Well, they have a machine that just basically does all that math for them, right? But more specifically, they find out this whole launch angle thing, that how fast the ball is exiting at a certain angle, they're done. They can almost predict where it's going to go. Now, the one thing that they do have to take into account is air resistance, but that's why they have a computer that goes super fast with it. That's why they have engineers that go into and figure out all of that calculation stuff, so it's already done for them. It's how does a golfer know what to hit at a certain point? Well, how hard they swing, the angle at which that club is figured in. If you're a professional golfer, your swing's pretty constant. If you're a hacker, like the majority of us, not so constant. So you're like, wow, that one went a lot farther than it's supposed to. Yep, sometimes that happens. Or, yeah, that didn't go where it was supposed to. And it's, I call them worm burners, where they just go right across the ground. Burning all the worms on the ground. Okay? It's those things. Why do we know those? And it's the same thing in, say, like track and field. Like, how do we know long jumpers are going to go farther if they're faster? They go further because if their horizontal velocity is faster, they're literally going to go farther. Why do we want our throwers to launch it at a certain angle or roughly to it in the throws so that they're maximizing this here so that it maximizes that there. Because if you launch it up too high, it just kind of, just like if you were throwing something up there, you launch it up here, it's not going up very far, right? You throw it straight across, you're still not maximizing it perfectly. That's why I love sports. Watching sports at a high level sports, because there's so much there. It doesn't matter what it is. I love watching it because it's all stuff with this.